Grounding both the unit and the wire is generally required for safety and performance reasons. For unit grounding, connect a grounding wire, typically green or bare copper, from the metal frame or enclosure of the electronic device to a dedicated grounding rod driven into the earth near the base of the building. This provides a direct path for fault currents to the ground. For wire grounding, run a separate grounding wire from the CAT5e cable shield, whether it's foil or braid, to the same grounding rod used for the unit grounding. You can connect the grounding wire to the cable shield using a grounding clamp or connector. The reasons for grounding are primarily threefold. Firstly, safety. Grounding protects against electrical shocks by providing a path for excess current to flow to the earth, preventing it from passing through the device or a person. Secondly, noise reduction. Grounding minimizes electrical noise by dissipating it to the earth. This can improve the performance and reliability of the electronic device, preventing data corruption or signal interference. Thirdly, surge protection. Grounding helps protect against voltage surges, such as those caused by lightning strikes or power fluctuations, by providing a path for the excess energy to dissipate safely. Some additional considerations to keep in mind are: firstly, using a high-quality grounding rod, typically made of copper-clad steel or solid copper, to ensure effective grounding. Secondly, ensuring that the grounding connections are tight and secure to maintain a low resistance path to ground. Thirdly, grounding should be carried out by a qualified electrician to ensure proper installation and adherence to local electrical codes such as the National Electrical Code, NEC, 2008, and to guarantee safety. If the CAT5e cable is used for data transmission only, grounding the wire may not be absolutely necessary, but it is still highly recommended to ground the unit itself to provide a safety ground for the equipment. Even data cables can potentially carry stray voltages. If the electronic device is not enclosed in a metal frame, you may need to create a grounding point using a grounding block or a similar device to provide a suitable connection for the grounding wire. The size of the grounding wire depends on the overcurrent protection of the circuit. Consult NEC Table 250.122 for the minimum size of grounding conductors for alternating current systems. The minimum size of the grounding electrode conductor is based on the size of the service entrance conductors according to NEC Table 250.66. All grounding connections should be accessible for inspection and testing. Check grounding connections periodically to ensure they are secure and free from corrosion. Properly installed grounding systems minimize the risk of electrical hazards and enhance equipment performance. Bonding is also important, which involves connecting all metal parts of the electrical system to create a path for ground fault current. Grounding ensures a safe path for fault current to flow back to the source, tripping the circuit breaker and energizing the circuit. Use appropriate connectors and clamps to ensure proper grounding. Verify the effectiveness of the grounding system with a ground resistance tester. Consider using surge protection devices in addition to grounding to protect sensitive electronic equipment. Consult with a qualified electrician or electrical engineer for assistance with complex grounding systems. Grounding systems should comply with all applicable electrical codes and regulations, including NEC 2008. Proper grounding is an essential safety measure that helps prevent electrical shocks and equipment damage. The 24-volt DC device, while low voltage, can still pose a hazard if not properly grounded, especially in wet or outdoor environments. The grounding wire should be as short and straight as possible to minimize impedance. Avoid creating ground loops, which can introduce noise into the system. Label all grounding connections clearly for future reference. Regularly inspect the grounding system for damage or corrosion. Grounding helps to equalize the potential difference between different parts of the electrical system. Follow manufacturers' recommendations for grounding electronic equipment. Grounding is particularly important in areas with high lightning activity. Consider using a lightning protection system in addition to grounding. Grounding can also help to reduce electromagnetic interference (EMI). A properly grounded system can improve the overall reliability of electronic equipment. Grounding is a fundamental principle of electrical safety. Always prioritize safety when working with electrical equipment. Grounding provides a low impedance path for fault current to flow to ground. The grounding electrode should be located as close as possible to the equipment being grounded. Grounding systems should be designed to minimize voltage drop during fault conditions. Ensure that the grounding conductor is properly sized to carry the maximum fault current. Grounding helps to prevent the buildup of static electricity. Static electricity can damage sensitive electronic components. Grounding is an important part of a comprehensive electrical safety plan. The grounding system should be tested regularly to ensure its effectiveness. Grounding is not the same as bonding, but they are both important for electrical safety. Bonding connects all metal parts of the electrical system together, while grounding connects the system to the earth. The grounding system should be designed to minimize the risk of electric shock. Electric shock can be fatal. Always disconnect power before working on electrical equipment. Grounding is an essential safety measure for all electrical systems. Proper grounding can help to prevent fires. Electrical fires can cause serious damage and injury. Grounding is an investment in safety and reliability. The grounding system should be designed to last for the life of the equipment. Grounding is a responsibility of all electrical professionals. Always follow proper grounding procedures. Grounding is a critical part of electrical system design. The grounding system should be designed to meet the specific needs of the application. Grounding is an ongoing process. The grounding system should be inspected and maintained regularly. Grounding is a key component of electrical safety. Proper grounding can help to prevent accidents and injuries. Grounding is a fundamental principle of electrical engineering. The grounding system should be designed to comply with all applicable codes and standards. Grounding is an essential part of electrical safety. Proper grounding can help to save lives. It's important to use appropriately sized grounding conductors and connectors to ensure effective and safe grounding. In accordance with NEC 250.4, electrical systems must be grounded in a manner that limits the voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines, and that stabilizes the voltage to ground during normal operation. This is essential for protecting both equipment and personnel. The size of the grounding conductor is determined by the size of the ungrounded conductors, as specified in NEC 250.66 and 250.122. The grounding electrode system should be designed to provide a low impedance path to ground, which helps to minimize voltage rise during fault conditions. According to NEC 250.50, all grounding electrodes that are present at each building or structure served must be bonded together to form the grounding electrode system. This includes metal underground water pipes, metal frames of buildings, concrete encased electrodes, and ground rings. The CAT5e cable, even though used for data, can still have induced voltages or serve as a path for fault currents if it comes into contact with a live conductor or experiences a lightning surge. Therefore, grounding the shield of the cable provides a safe path for these currents to dissipate, reducing the risk of equipment damage and electrical shock. When installing the grounding rod, ensure it is driven into the ground to a depth that provides adequate contact with the earth. The NEC requires a minimum of 8 feet of contact with the soil. Use a copper or copper-clad steel grounding rod that is at least 5/8 inch in diameter. The grounding electrode conductor, which connects the equipment grounding conductor to the grounding electrode, must be sized according to NEC Table 250.66 based on the size of the service entrance conductors. Grounding is not only for safety but also for ensuring the reliable operation of electronic equipment. By providing a stable reference point, grounding reduces the effects of electromagnetic interference and voltage fluctuations, which can cause data errors and equipment malfunctions. In industrial and commercial settings where multiple pieces of equipment are interconnected, it is especially important to establish a well-designed grounding system to prevent ground loops. Ground loops can create circulating currents that interfere with signal transmission and can even damage equipment. NEC 250.96 requires that all metal enclosures containing service conductors be effectively bonded together into the grounding electrode system. This includes enclosures for transformers, switchgear, and other electrical equipment. When using a metallic conduit to protect the CAT5e cable, ensure that the conduit is also properly grounded and bonded to the equipment grounding system. This provides an additional layer of protection against fault currents. If the building has a lightning protection system, it is important to bond the grounding system of the electrical equipment to the lightning protection system to ensure that lightning currents are safely conducted to ground. This bonding should be done in accordance with NEC 250.60. In some cases, it may be necessary to use a separate grounding electrode system for sensitive electronic equipment to minimize the effects of noise and interference. This is known as an isolated ground system and is typically used in hospitals, laboratories, and other facilities where precise measurements are critical. According to NEC 250.146, the grounding inductor for an isolated ground receptacle must be run directly back to the main grounding electrode system and must not be connected to the normal equipment grounding conductor. Regular inspections and testing of the grounding system are essential to ensure its continued effectiveness. This includes visual inspections to check for corrosion, loose connections, and damaged conductors, as well as electrical tests to verify the impedance of the grounding system. When performing electrical work, always use appropriate personal protective equipment, PPE, including safety glasses, gloves, and insulated tools. Follow lockout/tagout procedures to de-energize the equipment before working on it. If you are not qualified to perform electrical work, hire a licensed electrician to do the job. Electrical safety is everyone's responsibility. Be aware of the hazards and take steps to protect yourself and others. Proper grounding is a critical component of a safe and reliable electrical system. By following the recommendations in the NEC and using best practices, you can help to prevent electrical shocks, equipment damage, and other hazards. In the context of the 24-volt DC electronic device, grounding serves to ensure that the chassis or enclosure of the device is at the same potential as the earth, preventing any potential difference that could lead to a shock if someone were to touch the device while also in contact with a grounded surface. Grounding the CAT5e cable shield, especially when run outdoors or in environments susceptible to electrical noise or surges, offers protection against induced voltages or transient surges that could damage the connected equipment or disrupt data transmission. The choice of grounding method and components such as grounding rods, clamps, and conductors should adhere to local electrical codes and regulations, as well as manufacturer recommendations for the specific equipment and cable being used. Grounding systems should be designed and installed by qualified personnel to ensure effectiveness and safety. NEC Article 250 provides comprehensive guidelines for grounding and bonding electrical systems, including requirements for grounding electrode systems, grounding conductors, and equipment grounding. In addition to safety and performance benefits, proper grounding can also help to extend the lifespan of electronic equipment by protecting it from voltage surges and other electrical disturbances. In telecommunications applications, grounding is particularly important to minimize noise and interference, which can degrade signal quality and reduce data transmission rates. When installing a grounding system, it is essential to consider the soil conditions and the presence of any underground utilities or structures. The grounding rod should be driven into the ground at a location where the soil is moist and conductive, and it should be placed away from any buried pipes or cables. Proper grounding is a fundamental aspect of electrical safety and should never be overlooked. By following the recommended practices and guidelines, you can ensure that your electrical systems are safe, reliable, and perform optimally. NEC 250.4 covers general requirements for grounding and bonding, including the requirement that electrical systems be grounded in a manner that limits the voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines, and that stabilizes the voltage to ground during normal operation. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. The grounding electrode conductor must be made of copper or other corrosion-resistant material and must be protected from physical damage. When connecting the grounding electrode conductor to the grounding electrode, use a listed connector that is suitable for the application. Ensure that the connection is tight and secure and that it is protected from corrosion. The grounding electrode system should be tested periodically to ensure that it is providing a low impedance path to ground. The test should be performed by a qualified electrician using a ground resistance tester. If the grounding system is not performing properly, it should be repaired or replaced as necessary. NEC 250.52 specifies the types of grounding electrodes that are permitted for use in electrical systems. These include metal underground water pipes, metal frames of buildings, concrete encased electrodes, and ground rings. The grounding electrode must be installed in accordance with the manufacturer's instructions and must be protected from physical damage. When using a metal underground water pipe as a grounding electrode, it must be electrically continuous and must be connected to the grounding electrode conductor within 5 feet of its point of entrance to the building. When using a metal frame of a building as a grounding electrode, it must be effectively grounded and must be connected to the grounding electrode conductor at multiple points. When using a concrete encased electrode as a grounding electrode, it must consist of at least 20 feet of bare copper conductor that is encased in concrete and is located near the bottom of the footing or foundation. When using a ground ring as a grounding electrode, it must consist of a bare copper conductor that is buried in the earth in a ring around the building. The ground ring must be at least 20 feet in length and must be buried at a depth of at least 2.5 feet. Grounding is a critical aspect of electrical safety and should never be taken lightly. By following the recommendations in the NEC and using best practices, you can help to prevent electrical shocks, equipment damage, and other hazards.